KD trees is something that you do when you have low-dimensional data. When you have high-dimensional data, there is a similar technique, which is quite different, but it has some similarities. It's called locality-sensitive hashing. It operates at a high level in roughly the same way. What I'm going to do is I'm going to take my space and I'm going to cut it up into regions, just like a KD tree did, only this time my regions are going to look different. What I'm going to do is I'm going to start drawing random hyperplanes through the space. So in 2 dimensions, I'm just drawing lines, and these lines are completely random. Okay? So what I'm doing is, as I draw the first line, let's say that that's my hyperplane, that hyperplane is going to cut my space into 2 regions. So a positive region here and a negative region here. When I add a second hyperplane, now I have 4 regions. All right, so I look at the intersections of the hyperplanes and the little regions that are defined by those intersections. So now I have 4 little regions, and as I add regions, when I introduce k hyperplanes into the space is going to get cut up into 2 to the power of k regions, because that's how many combinations you have of whether I'm on the left or the right side of each hyperplane. So it's 2 choices at each time, repeated k times, so you get 2 to the k regions. Each region is going to be a polytope, so it has linear sides. It's bounded by hyperplanes on all ends, and they're mutually exclusive. So a point is going to fall into one and only one of those regions, and just by looking at them, you will see that the points in a particular region are, by definition, kind of close to each other. Right? Because you're cutting the space into smaller and smaller regions, so whatever happens to be in a fairly small region must be reasonably close to each other. Now note, of course, that you're not guaranteed that nearby points end up in the same region. So, for example, this point and that point, they're quite close to each other, but they could easily end up on opposite sides of the hyperplane and in 2 different regions. So, and then what you do is when a testing point x comes along, you only compare it to the points that fall within the same region as that testing point. So you take the testing point, you figure out which side of each hyperplane it falls into. That tells you that the testing point is going to be, say, in this region of space, and then you only compare it to the training points that also fell into that region of space. So what you've done is you've taken the space, cut it up into some buckets, and then you only compare to the training points within the same bucket as the testing point. So the complexity of this is attractive. The overall complexity is it takes about kd plus dn over 2 to the k operations, and I'll walk through where that figure comes along. So if you set k to be on the order of the log of n, the overall complexity comes out to be about d log of n. So it's the same kind of complexity that you had for the kd tree, right? It's a lot more attractive than dn, which is the brute force way of doing nearest neighbors. Right? You're talking about it's logarithmic in the number of training examples as opposed to linear in the number of training examples. So it's significant saving in terms of time. Now, where does this complexity come from? When you're using LSH to find nearest neighbors, there's 2 steps that you need to do. First, you take your training point, you take your testing point, the red dot, and you have to figure out which bucket it falls into, which region of space it falls into. And for that, what I need to do is I need to compare that point to every hyperplane and figure out, is it on the positive or on the negative side of that hyperplane. And I need to do it for all the hyperplanes in order to find one region. So I have k hyperplanes. The points are d-dimensional, so it's going to take k times d operations to compare the testing point to all the hyperplanes, to find the buckets. So that's the cost of finding which region, which sort of subspace the point falls into. Once you know which region you have fallen into, you have to do a comparison inside the region. Now, why do you have to do that? The reason you do that, remember, this region, it's only an approximate. These are your potential candidate nearest neighbors. They're not guaranteed to be real nearest neighbors, and some of them, like these points there, they can end up being quite far from the testing point. what you want to do in that case is you want to do direct comparisons. So you identify points that are really nearest neighbors and throw away the ones that accidentally ended up in the same bucket, in the same region of space. So you need to do those comparisons. And how many of those comparisons you're going to have? Each comparison is going to take d operations, because that's the dimensionality of your vector space. And how many neighbors you're going to have? Well, that's pretty simple. If you have k hyperplanes, you're going to cut up the space into 2 to the power of k regions. And if the overall space contained n instances, then a randomly picked region is going to contain n over 2 to the k elements in it. Okay, so so d times n over 2 to the k, that's the cost of comparing your testing instance to every one of the training instances that are in the same bucket, and there are n over 2 to the k of those instances. Okay, so that's the computational cost. Now, again, this comes with a price. Because of the way you're cutting up the space, you can easily miss nearest neighbors. So this data point that's circled in red happens to be on the opposite side of several hyperplanes, so there's no chance that I'm going to find it with this technique. With LSH, you have a mechanism to temper this problem, the false negative problem, the missed nearest neighbors problem. And what you do is you repeat the whole procedure L different times, but with a different set of hyperplanes. So this is just one particular set of hyperplanes, the red, the green, and the blue. If I picked 3 different hyperplanes, they will cut the space in a different way. And maybe in that different partitioning of the space, I'll be able to find that missed nearest neighbor. So it's quite similar to KD trees. It's quite different in other respects. I'm not going to dwell on it, but you should pause and think why does this even exist? Why is it not right to just use KD tree everywhere? Because both of them cut up the space, and KD trees seem to cut up the space in a way that's a lot more natural. Right? You just pick the median, you're guaranteed to have half the points on the left and the right side each time, and here you're doing some random funky cutting thing. So why is this even necessary? It is. So try to puzzle out why.